Okay, the final structure to talk about is the LSTM, or long short-term memory. So the basic idea is that we're going to both hold our short-term memory, just like in recurrent neural nets, in these H vectors. So we have H1, H2, H3, and so on. All of them, just like in recurrent neural nets in the basic RNN, have X1, X2, X3, and so on as inputs to those hidden states. Then, just like in RNNs, those hidden states are going to be determined along with the input are going to be used to determine the output and the logits, which would be then used for logistic regression loss functions, multi-class logistic regression loss functions. The S's in this case are these long-term memory cells or memory states, which are vectors also. Which are also vectors in RD, or some other dimensionality. And the distinction between S and H really are in the fact that the S's are intended to maintain a long-term memory, whereas the H's are intended to maintain short-term memory. So the issue with the RNN in general is that oftentimes it will forget sort of what happened at the beginning of a sentence when you're pretty far along in the sentence. So this context, this long-term context, is forgotten. So the addition of long-term memory states, hidden units, is intended to remedy that. So what is, how does this structure, how is it created to make it so that S is actually long-term, does correspond to long-term memory, and H corresponds to short-term memory? So the first thing to note is that the short-term memory, the first thing that we do is we combine it by concatenating it. So we have our H sub t minus 1 is input for the LSTM cell. Another input is the X sub t, and those get concatenated together so that when we form linear functions of this concatenation, that's just the sum of linear functions of the individual components. So the first thing that we can see that it gets inputted into is a sigmoid layer. So you think of this as a fully connected linear layer with a sigmoid activation function. So what does that do? That creates something that's between 0 and 1. We can see an example here. We have our H sub t minus 1 and our X sub t are both inputs, and then we have our linear function of that. Let's just give that a temporary variable name alpha sub t. Then we can apply a sigmoid to it. Now that creates this beta sub t. So beta sub t is a number between 0 and 1 because it's a sigmoid. Then what are we going to do with this? Well, this number between 0 and 1 is going to multiply the S sub t minus 1, the long-term memory. It's going to multiply it. What that ends up doing is it forms like a forget gate. It just dampens it because it's a number between 0 and 1, and it multiplies this S sub t minus 1. So this forget gate multiplies this S sub t minus 1, and then this thing gets added to something. But we have to update this long-term memory. So how do we do this? So we take our hidden state and our input and we apply it through a tanh layer. So this is also a fully connected linear function with a tanh activation function. And then we also form a sigmoid layer, and then this element-wise multiplies that tanh. Now we have our update for this long-term memory. So then we add it to the long-term memory, and that forms our new long-term memory S sub t. Right? Okay, so now that we have this, how do we use this to update the short-term memory? Well, we're going to pass it through another tanh function, and then we're going to use a sigmoid activation function as another gate. So we have the sigmoid of X and H, and then this will update the H sub t, the short-term memory, by as another forget gate. So this will form our H sub t, our short-term memory, and then that also is used for our output. And so that's what that's what goes as input for our loss function, and that's really what how the supervising variable updates this entire thing. Now, it might seem that there are a lot of different units which will create a lot of different parameters here. But there are sort of two things to think about when we're talking about this. First of all, the typical corpus that's going to be used to train a neural translation model is going to be massive. It's going to be very large. So we're not just talking about the size of capital T, the number of words in a sentence, but really the number of sentences is what's going to make it so that we can actually train this thing. And a corpus is extremely large, the types of corpuses that we use to train these models. So that's the first thing to mention, is typically we use very large data sets to train these things. And second of all, it's not like all of these have to necessarily have a lot of dramatic updates to their parameters for this to be a reasonable model. If we update some units with zeros, then if those units don't get changed, if those weights which are zeros, or biases which are zeros, if those don't get changed, then it's as if they never existed in the first place. So it's really just a more general model that if it gets updated, then the hope is that that will be something advantageous to the performance of the model. So LSTMs were sort of one step along the way of forming modern neural translation models. LSTMs have some good performances, but recently more something called the attention mechanism has been introduced to deep neural nets, and this forms modern transformer models, which are used for neural machine translation. So that's the basis for modern neural machine translation and natural language processing in general. And now these attention mechanisms and transformer models, which I encourage you to go look at, those are used in a lot of modern recommendation systems and natural language processing.